Hello, welcome to another college math video. In this video, we're going to begin our journey with probability. This first video in particular is really just the general overview on anything and everything probability, which will lead us into the more complex stuff as we continue on. So our objectives for this video: review vocab and concepts related to probability and theoretical probability, and then solve problems involving both of those things, theoretical and empirical probability. The difference between them is very slight, but we make the difference in this first video, and then we really don't worry about it too much moving forward. Okay, so some notes. As is often the case in these first videos, we've got to get a lot of background information, just lay the framework for what it is we're looking at. So an experiment. This is something that we will kind of use throughout the chapter. You'll typically imagine an experiment to be very scientific in nature, but it's very general. So an experiment, for our purposes, a controlled operation that yields a set of results. So this definition does work for the more complex scientific types of experiments. Those are not what we're doing in here. This is very simple as you roll a die. That is a controlled operation that yields a set of results. Okay, outcomes. These are the possible results of an experiment. We will only do or look at experiments with outcomes that we know are possible. So rolling a die, for example, the possible outcomes are rolling a 1, a 2, a 3, a 4, a 5, or a 6. We're not looking at experiments where we don't really know what would happen from it. We'll know rolling a die, choosing a card from a deck. We know what the options are in a deck of cards. And if you don't remember right now, we will talk about it in detail. And then our last definition before we really get into the probability stuff is an event. This is a subcollection of the outcomes of an experiment. Subcollection of the outcomes of an experiment. So we'll have an experiment like rolling a die. The different outcomes are 1, 2, 3, 4, 5, or 6. An event, subcollection of those, would maybe be rolling a number greater than a 4. It's a collection of some, maybe only one, but sometimes more than one, of the outcomes. An event rolling a number higher than 4. That's something that you could hope for when rolling a die. So keep those things in mind as we move forward. Okay, so the first of the two we're looking at, empirical probability. This is also known as relative frequency. The definition here, it's kind of boring, but we'll list it. They also call it relative frequency because empirical probability is the relative frequency of an occurrence of an event. We're going to add another note there. Relative frequency of an occurrence of an event. And this is what distinguishes empirical from theoretical probability, is that empirical is determined by actual observations. It sounds complicated. I promise it's not. And you'll see that in the example. But let's just look at what the problem would look like. So we'd have the probability P of E. You can read that as P of E, or the probability of E, where E is the event, whatever the event might be, rolling a number higher than 4, something like that. That'll be defined. Then you'll just give it a letter. And it's two numbers, a numerator, denominator. The bottom number is always easier to focus on first, the total number of times the experiment was performed. Remember, this one is based on actual observations. So the thing we're looking at has already happened a bunch of times. How many times was it attempted before? That's your denominator. And then of those number of times the experiment was performed, how many times did the event you want occur? 2 numbers. Get denominator of those 20, how many times did the thing we want actually happen? Actual observations. So let's see an example of that. You play table dominoes, which is a game that originated in China, 100 times. 44 times you lost, 56 times you won. What's the empirical probability of losing on the next time that you play? Okay, the event that we're looking at is losing. So we'll call this event L. So the probability of losing, P of L, however you want to read it, numerator and denominator. Denominator is the total number of times the experiment was performed. The experiment in this case is playing the game. You played the game 100 times. Of those 100 times, get the numerator. How many times did the thing we're looking at, which is losing, did that happen? 44 times you lost. 44 over 100. That's it. If we didn't know this background information on losing and winning, we might assume that we have an equal chance of winning. So it's the probability of losing. We might say 1/2 if chances are equal. But this is based on previous information. We know we're actually pretty good at this game. So 44 times we would lose, 56 times we would win. We've got a slightly better chance of winning. So ultimately the probability of losing on your next game, out of the 100 times it's already happened, you lost 44 times. So that's what we would expect moving forward. So in this section, an online homework system will be specific with you, but typically they're just going to want simplified fractions. So you can do it by hand, but you can also do it in the calculator. There's a couple different ways. If you're using something like a TI-83 or an 84, something that looks like this one, you can just type in that division, 44 divided by 100. The calculator is always going to spit out a decimal at you. Sometimes an online homework system will ask for a decimal. Most of the time it won't. We're going to go with simplified fractions. So it gives you a decimal. Then you will hit a button on the calculator that says math. Somewhere up in the top left-hand portion of the calculator, hit the math button. The first option you see is an arrow and then the letters FRAC. And that means change to fraction. So this is what you're seeing. I suppose it might not be the first option, but most likely it is. This means change to fraction. So you hit enter on that one because that's what we want. Then the calculator says answer, which means take my answer, change it to a fraction. You hit enter, and it gives you the simplified version of the fraction, which is 11 over 25. You might be able to do it by hand, and that's great. Maybe you looked at this and you said 22 over 50. If you left it here and that's what you typed in, I promise you it would mark it wrong because it's looking for the most simplified version. Anytime you're simplifying, it's always the most simplified fraction. Many people feel very uncomfortable with fractions, and I promise you, you can always type it in the calculator and have it simplify. You do not have to do that part by hand. If you're using something like a TI-30, you'll see something like this. It might not be a button, it might be above one of the buttons, but this means going back and forth between fraction and decimal. So you can do the same thing, type 44 divided by 100, and then look for that button, wherever it might be in the calculator, click that, and it'll say take my answer, change it between fraction and decimal, and it'll spit out the simplified version. Some of your calculators will just automatically give you the simplified, and that's fantastic. But ultimately, we really are looking for simplified versions. Okay, so that's what empirical probability looks like, based on previous information. Okay, so practice problem. This is empirical probability. 500 Italian students were surveyed about their gelato preference. Vaniglia or vanilla was chosen 123 times. Bacio hazelnut chosen 258. Fragola strawberry chosen 50 times. Pesca peach chosen 10 times. And then none chosen 59 times. So find the empirical probability of each. Go ahead, pause the video and work through these. Remember, simplified fractions are what we're looking for. Okay, so let's see if we're on the same page. The first one we're looking at is Vaniglia. I'll call this event V. The probability of Vaniglia being chosen on the next student coming in. There were a total of 500 students surveyed. Of the 500, how many did what we wanted, which was choose vanilla? 123. And this one, type in the calculator, hit change fraction, decimal to fraction, doesn't simplify. So this is as good as this one gets. The next one, the next event is Baccio. I'm going to call it event B. If you called it event H, that's fine, as long as you kind of indicated that that's what you're doing. So probability of Baccio, out of the 500, 258 chose Baccio. 258 divided by 500, change to fraction. The simplified version is 129 over 250. The third is Frajola. We'll call this event F. Probability of Frajola being chosen next. Out of the 500 that we already saw, 50 picked Frajola. 50 divided by 500, change to fraction. 1 in 10 will choose Frajola. The next one is Pesca Peach. Probability of peach being chosen of the 500, 10. We get 1 over 50. And then the last one, none. Probability of none. Out of the 500, we had 59 choose that, and I don't think that simplifies. Nope, that's as good as that one gets. So those should be what your 5 answers look like here. You were asked to leave them as a fraction, so this is ultimately how they should be, and we were looking for all 5 of them. So sometimes you'll only be asked about one. It just depends. But the main thing to keep in mind is that empirical probability is based on stuff that already happened, not necessarily what might happen. We are looking at what's happening moving forward, but it's based off of what already happened. So let's compare that to theoretical probability. Typically, we just say probability when we're talking about theoretical probability. And honestly, we'll just start to say probability even when we mean empirical long term, because both will kind of get mixed. But this is where we see the differentiation. Theoretical probability, again, pretty general definition. It's a study of the possible outcomes that can occur for the given experiment. A study of the possible outcomes that can occur for the given experiment. So this has nothing to do with what's already happened. This is all about what's possible moving forward. When you're rolling a die, there's an equal chance of all 6 numbers landing. If you ran an empirical probability question on it, it might be the case that you just so happen to roll a 6 10 times and a 5 5 times. Who knows? And then you would use that. But theoretical, there's an equal chance of each thing happening. So that's what we use moving forward. Okay, again, the formula has the same feel. We read this as P of E, or probability of E, where E is the event. E might be rolling a number greater than 4, might be choosing pesca as your gelato, who knows. And the two numbers, numerator and denominator, again, same feel. The denominator is the total number of possible outcomes. So not how many times the thing already happened, but how many different ways could the thing occur. And then of those, how many are favorable to your event, whatever your event might be. That'll always be defined. Okay, before we do some examples with this, let's just list a couple facts about probability. There's 4 that we're going to discuss here. The first one, the probability of an event that cannot occur. Is, what do you think it is? For the first 2, I just want you to think about the example of rolling a standard die. It has 1, 2, 3, 4, 5, 6. If I said, what's the probability of rolling a number greater than 8? You have 1 die, you're rolling it 1 time. There are 6 options when you roll the die. That's your denominator. Of those 6, how many meet the criteria of being greater than 8? None of them, right? This is a thing that can't occur. If you roll a die one time, you can't get an 8. If you're playing a game where you're adding all of your rolls up and the last roll you need an 8, well, it's over. That event can't happen. The probability of an event that cannot occur, simplify this, is 0. 0. The second fact, the probability of an event that must occur is, let's think about this same problem. We're rolling a die multiple times and we're adding the numbers up, and now we want a really small number, let's say. So on our last roll, let's say we've done very well. We just need something that's less than 8. As long as we get something less than 8 on our last roll, we win the game. Well, we still have 6 options when we roll the die. Of those 6, how many meet this criteria of being less than 8? 1, 2, 3, 4, 5, 6. All of them are less than 8. So 6 out of 6, which simplifies to 1. It's going to happen. So the probability of an event that must occur is 1. So those are the two far ends of the spectrum. You have an event that definitely won't happen, getting a number greater than 8 on a standard die. That's 0. Or an event that's definitely going to happen. Probability would be 1, rolling a less than 8 on one roll. So between 0 and 1. The third fact is essentially that. Every probability is between 0 and 1 inclusive. Inclusive because we just saw it's possible to have a probability of 0 and it's possible to have a probability of 1. So every probability that you're finding is somewhere between there. Now it's kind of difficult to assess what that would look like because we have fractions. Anytime you have a number, you can also look at it as a decimal, and you should have 0 through 1. If the number is higher than 1 and the question is what's the probability, then something totally went wrong, because you cannot have a probability greater than 1 or less than 0. It's going to be somewhere in between, including those two endpoints potentially. All right, and then the last fact, which we will look at a little bit more on our next example, is that the sum of all probabilities of all possible outcomes is 1. This is essentially taking the probability of each different thing that could happen when we're rolling a die. Probability of rolling a 1 is 1 out of 6. Of rolling a 2, 1 out of 6. Rolling a 3, 1 out of 6. If we add up all of the different potential outcomes probabilities together, we're going to get 1. I'll prove it to you on the next example. All right, so let's see another example. Let's say we have a bag that has 5 2-euro coins, 2 1-euro coins, 8 50-cent coins, and 1 5-cent coin. So here are what the euro coins look like. We're choosing one randomly, so they're in a bag. And yes, technically your hand might be drawn to the larger or the smaller. We're going to assume that there's an equal chance of each one being selected. So one gets selected. What's the probability of choosing? We'll start with a 20-cent coin. So we'll call this event T for 20-cent coin. The probability of T. First, we need to know denominator. How many different options are there when we put our hand in the bag? 5 of this one, 2 of this one, so 7, 8 of this one, so 15, and 1 of this one. So there's a total of 16 different coins in the bag. Of those 16, how many meet our criteria, what we're looking for, which is a 20-cent coin? And it looks like none of them. 0 out of 16, 0. So this, again, just proves that first fact. The probability of an event that cannot occur is 0. Now, going into the game, let's say it's a game where you have all these coins and you're trying to pick a certain one, you might not know what the bag has, but the person running the game would know, and they would know there's no 20-cent coins. So when you say, I'm going to shoot for a 20-cent coin, they know you already can't win. They might tell you all the coins are in there, and maybe they are, maybe they're not. Who knows? Okay, the second one, we're looking for probability of a €1 coin. We'll call this event O. Probability of a €1 coin. Again, there are 16 coins in the bag, 5 of this, 2 of this, 8 of this, 1 of this, 16 total. How many meet the criteria of being a €1 coin? There are 2 €1 coins, so 2 out of 16 simplifies to 1 out of 8. So probability of selecting a €1 coin, 1 out of 8. Okay, how about a probability of a 50-cent coin? We'll call that F, probability of 50 cent. Again, it's out of 16. Of the 16, how many are 50-cent coins? In this bag, we have 8. So you would have a 1/2 chance of winning. You can use the calculator for those. I'm doing these in my head, but if you don't feel comfortable doing that, that's fine. It doesn't matter. Use the calculator if that's what you feel you need to do. Okay, the next one, a €2 coin. We've already used T, so we'll call this a W. So probability of a €2 coin. We still have 16 options. These are all just different games, like we're starting over every time. We'll get into eventually multiple selections, but not yet. €2 coin, we have 5 of those, so 5 out of 16. That one doesn't simplify, so that's as good as it gets. And our last event is a 5-cent coin. We'll call this V. Probability of V. Out of the 16, how many are 5-cent coins? We have 1, so 1 out of 16. Okay, then the question, what's the sum of these probabilities? If we add them all up, and for adding purposes, I'm going to go with the non-simplified. We have 0 over 16 plus 2 over 16 plus 8 over 16, 5 over 16, and 1 over 16. If they have the same denominator, we can add the numerators. 0 plus 2 plus 8, 10 plus 5, 16 plus 1. 15 and then 16. 16 over 16, which is 1. This just proves again the sum of all the different possible options, probabilities, will always add up to 1. Even when we add in the stuff that's not possible to happen. And there's lots of variations on things that could be asked in a situation like this, but for now we're just keeping it basic. Okay. All right, so let's do some practice then. We've got 2 problems. We'll do one, so go ahead, pause the video, go through. Let's just talk about the standard deck of cards first. If you're not familiar, this is something that you're going to have to be familiar with for this chapter. You can Google standard deck of cards, and it'll show you the whole deck all at once if it's easier for you to look at it. But in general, there are 52 total cards, and that breaks down into different suits. There are 13 clubs, 13 spades, 13 hearts, 13 diamonds. And then within each of those 13, we have ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So imagine you've got that whole deck in front of you, or it's shuffled. You're going to choose one randomly, find each individual probability. So go ahead, pause the video. We'll see if we're on the same page in a moment. All right, let's see what you got. So one card is being selected randomly from the deck. 4 different scenarios happening. The first one we're looking for is the probability that the card you choose is a heart. So we'll call this event H. Probability of H. Okay, so when you make your selection, first the denominator, how many choices do you have? There are 52 total options. The entire deck is there. Of those 52, how many meet your criteria of being a heart? Well, the deck is broken down so that 13 of them are hearts. Then we simplify. By hand in the calculator, doesn't matter, we get 1/4. If you're looking for a heart, you have a 1 in 4 chance of selecting a heart. All right, the second one, a heart and a diamond. I'll call this A for and. Probability of A. You're selecting one card. You have 52 choices when you pull the card. Of the 52, how many meet this criteria of being both a heart and a diamond? Don't let the question fool you. How many cards are both heart and diamond? There are no cards that are both heart and diamond. Heart and diamond are totally separate suits. So there are cards that are hearts, there are cards that are diamonds, but there are no cards that are both. It is possible for cards to meet more than one criteria. It could be a heart and a 5. That's possible. But these are both suits. 13 club, 13 spade, those are separate. 13, 13, 13, 13. You cannot have both. So kind of a trick question, but it's, again, to keep in mind those differences between and or. And means both things, or one the other, or both. If that's possible, it just depends. So 0 out of 52 is 0. This is the probability of an event that can't occur. When you pull one card, you can't get both a heart and a diamond. Okay, next one, probability of an 8. I guess I'll call it E for 8. Again, we have 52 choices. How many of those choices are an 8? So of the 52, we have the 4 suits. And in each suit are all of those cards. So there's an 8 of clubs, an 8 of spades, an 8 of hearts, and an 8 of diamonds. So there are a total of 4 8s. If you're really struggling to visualize this, just pull up another tab, open up Google, pull up the entire deck. It'll show you the whole deck. You can count how many 8s there are. There are 4 of them. This simplifies to 1 over 13. And then the last one, 7 or a 10. This is O. We'll call this event O. Probability of 7 or a 10. There are 52 cards total. How many of the 52 are either a 7 or a 10? Sure, also or both, but they're in the same kind of category, so you won't have a card that's a 7 and a 10. So we have 4 7s. You can look through the whole deck and count them. And we have 4 10s. None overlap, so all 8 are possibilities. Imagine you're playing a card game where the whole deck exists. Okay, the last thing you need is either a 7 or a 10 and you win the game. You have an 8 out of 52 chance of that happening. This simplifies to 2 over 13. Should always be simplified in the end. Again, if you're not familiar with the deck of cards, I cannot emphasize enough how this chapter uses a lot of card playing questions. Online homework systems and these videos, you're going to have to be somewhat familiar with that deck of cards, or at least be able to pull it up and get used to using it. Okay, one more practice problem. This is comparing if medicine was taken to how long someone's cold was in days. So we have information. There were some people that took medicine, had a cold length of this long, some that didn't. 19 had a cold length of 1 to 3 days, 4 to 7 days were 79. So we're looking for each of these individual probabilities. So go ahead, pause the video, give it a shot. Let's see if we're on the same page. Okay, so 3 questions about this chart. We're first looking for what's the probability that medicine was taken. We can see from the bottom here, there were a total of 200 people that were involved in this survey. 102 did take medicine, 98 didn't take medicine, that adds up to 200. And of those same people, 105 had a cold length 1 to 3 days, 95 had 4 to 7. Again, total of 200 people. Studies are done like this all the time, and there's lots more statistical and probability type analysis you can do on it. We're not going into those deep things, just these general looks. So first thing is the denominator. There were 200 total people in the survey. Of those 200, how many took medicine? We're looking for probability that medicine was taken. So 86 had this cold length, 16 had this cold length, but there were 102 that took medicine. Whether you add up 86 and 16 or just look at the 102 there, then you are good to go. So 102 over 200, which simplifies to 51 over 100. There's the first one. I'm going to list the second one over here. Second question is, what's the probability that the cold length was 4 to 7 days? So still we're looking at all 200 people in the survey. Of those 200, how many had a cold length of 4 to 7 days? 4 to 7 days is right here. So we're concerned with everyone falling in this category. Some did, some didn't take medicine. Ultimately, we just want to know how long the cold was. 95 had a cold length of 4 to 7 days. So 95 out of the 200, which simplifies to 19 over 40. And then the last one, what's the probability someone in the study had no medicine taken with a cold length of 4 to 7 days? So we still have all 200 people to consider. Of those 200, how many met this criteria? No medicine taken with a cold length of 4 to 7 days. A little bit more specific. This one is no medicine taken. This is cold length 4 to 7 days. They overlap right here. Those are the people who did not take medicine and had a cold length of 4 to 7 days. So of the 200, there are 79 no medicine, cold length 4 to 7 days. And this one does not simplify. So this would be your final answer. Again, an online homework system will be specific if it wants a decimal or not. Most of the time, it's going to ask for the fraction. So I would consider that to be the standard way of presenting answers, where the question is probability. Okay, so this video just introduced the general idea of probability. We looked at the difference between theoretical and empirical, ultimately seeing that they have really the same feel. So moving forward, you can just keep the idea of general probability in your head. Always focus on the denominator first. How many different ways could this thing have occurred, or did it already happen? And then of that, how many meet your criteria, and that'll get your numerator. That line of thinking will help you even more as we progress through the chapter. I'll see you soon for another video.